Welcome to the third of what will probably be four videos in this algorithms notebook, or about algorithms. In this video, we'll be discussing a technique called memoization, which is related to an idea called dynamic programming, in which we use data structures to our advantage when calculating some kind of mathematical sequence, typically. When we have some kind of process where we need to first calculate, or where we need to sequentially calculate the results of elements in the sequence before we can calculate subsequent results. So let's look at an example of such a problem. We, in a previous notebook, wrote a function that would calculate the Fibonacci sequence. And in case you've forgotten, the Fibonacci sequence is calculated as follows. So the first number is 0, the second number is 1, and each subsequent number we calculate as the sum of the previous two numbers. So before we can calculate, say, the fifth number of the Fibonacci sequence, we need to first calculate the third and fourth, because the fifth is equal to the third plus the fourth. And when we see a formula like this, or can express a problem in a relationship like this, where the current result depends on the same formula but applied into past results. In other words, the way we calculate these things on the right, fn minus 1 and fn minus 2, are exactly the same as the way we calculate fn. We can think of f here as essentially, each time we calculate f in the same way. And this is what we might call a recursive formula, because we could expand fn minus 1 in the same way that we've expanded fn as fn minus 1 plus fn minus 2. So fn minus 1 would become fn minus 2 plus fn minus 3. Fn minus 2 would become fn minus 3 plus fn minus 4, and so on, until eventually we would hit f0 and f1, where we know what those numbers are because they are exactly specified. So we would step backwards from n until we eventually got to 0 and 1, which we know, and then we could sum up all the terms on the right-hand side here that we had expanded out. And this is essentially what happens in recursion. So we're going to now write a recursive formula for calculating the Fibonacci sequence. And it looks a lot like the formula we just looked at. To calculate the Fibonacci number n, or the nth Fibonacci number, if n is 0, then we return 0. That's exactly this equation right here. And if n is 1, then we return 1. That's exactly this equation here. Otherwise, we return the Fibonacci number, the n minus 1th Fibonacci number, and the n minus 2 Fibonacci number. And we add those together. So that's exactly this equation here. So we've expressed these three equations that specify the Fibonacci numbers in code. And because this function calls itself this function is recursive. So let's see how this works. So if I do Fibonacci 5, I get 5, as I would expect. What happens is 5 is not 0, and it's not 1, so we come down here, and we call Fibonacci recursive 4 plus Fibonacci recursive 3, which is also 5, of course. That's this result. So we make a call to this with 4, which is not 0 and not 1. So we end up with, for this call here, we end up with Fibonacci recursive 3 plus Fibonacci recursive 2. And on the right-hand side of this addition, we would have, again, 3 is not 0 or 1, so we would end up with Fibonacci 2 and Fibonacci 1. And we can see as I expand this out, we're getting the same result each time. And I'm essentially breaking down the stack of recursive calls to this function. So the sequence of recursive calls. So I'm going to expand it one more level, and then I'm going to say that's enough, because you get the idea. So here we have Fibonacci 3, which recursively calls, again, Fibonacci 2 and 1. Fibonacci 2 becomes 1 and 0. We have another Fibonacci 2, which becomes 1 and 0. And this Fibonacci 1 doesn't make a recursive call, because n equals 1 just returns 1. And we can see in most cases here, we're now reaching the point where we're not making recursive calls. We're hitting what we would call our base cases, where we can just return a definite answer, and we're not making any kind of call to the function again. This 2 will raise a recursive call, and we'll need to break that one down once again, but I'm not going to expand that out. And we see we get the same answer each time. So this is essentially what's happening when we call Fibonacci 5. It expands out into a set of function calls that eventually resolve to definite results. So I'll actually maybe expand this once more, just to show kind of how we would, or I'm not going to expand it more, but what I'll do is I'll replace these ones with Fibonacci 1 or 0 with the actual results, because these functions will just return 1 or 0. We don't know what Fibonacci 2 returns, because we would need to trace through the call stack until we eventually hit a 1 or a 0, at which point we would march back up the stack. So now we have essentially 1 plus 1 plus 1 plus 1 plus whatever this resolves to eventually. Now, let's, you might have noticed that as we were expanding this out, we compute some results more than once. We computed Fibonacci 2, 1, 2, 3 times. This is not very efficient because we're calculating the same things over and over. Let's see how many times we calculate each result for the 5th Fibonacci number. So here we're defining a function called Fibonacci count. And we're just going to essentially, for each time we count or make a call to Fibonacci recursive, so this is replacing Fibonacci recursive, and it's just expanding a little bit on the functionality. So we can see it still has if n equals 0, return 0. If n equals 1, return 1. And it still has these recursive calls. But we're adding in this dictionary, D, which is going to keep track of how many times we have seen a call for the nth Fibonacci number. So whenever Fibonacci count with some n gets called, we're going to increment the value in the dictionary at position n, or at key n, by 1. So if we run that Fibonacci count function, we see that to compute the 5th Fibonacci number, we computed the 4th Fibonacci number once, the 3rd one twice, the 2nd one 3 times, and then we made 5 and 3 calls to the 1st and 0th Fibonacci number, but there we don't actually need to calculate anything. We can just return the answer. So where we're really being somewhat redundant and inefficient is by recalculating the 3rd and 2nd Fibonacci number several times. And we can see we made this little tree here illustrating why this happens. So the 5th Fibonacci number breaks down into the 4th plus the 3rd. The 4th breaks down into the 3rd plus the 2nd. The 3rd breaks down into the 2nd and 1st. But here we have another 3. So we're breaking down 3 twice. And we pick up a 2 from the 4 and the 3, and another 2 from the 3. And we have to break all of those down as well. So this is essentially our recursive call stack here. And because we're making 2 recursive calls, as we step backwards through the sequence, we end up with this binary tree structure that branches out. And you can see at each level, as we step back kind of through the sequence, we're getting double the amount of calls. So the number of function calls we're making is growing exponentially fast. And some fraction of those are going to be redundant. If we could remember the result of Fibonacci 2, we would only need to make the recursive call once to actually calculate the result. Then we could store it, and anytime we needed it in the future, we could just simply reference the result we had already calculated. So for example, to calculate the 5th Fibonacci number, we would calculate the 4th. And to calculate that, we would need the 3rd and the 2nd. When we calculate the 2nd, we store that result in memory. To calculate the 3rd, we need the 2nd and 1st. We know the 1st, and we just calculated the 2nd. So we can now eliminate this level of call because we already know the answer here. So we eliminate these function calls. And then we add that 4th Fibonacci number, which we've just calculated, to the 3rd Fibonacci number. But we've already calculated that while we were calculating the 4th. So we can eliminate both of these levels of calls as well. So we trim out a huge portion of our call stack simply by storing the result that we already calculated in memory and referencing it if we can. As n gets larger and larger, this problem of redundancy is going to get even worse. So let's look at the 5th Fibonacci number, and we can see we are recalculating certain things tens of thousands of times. So this is really inefficient. We have to make a total of 75,000 calls to calculate the 25th Fibonacci number. So let's try and implement this idea that I've described of remembering what we've already calculated and calling upon it rather than making recursive calls. So we're going to now define this Fibonacci mem for memoized function. It still is going to be called with the number n for the nth Fibonacci number that we're going to calculate. And we're also going to pass in a dictionary D, where we're going to store results that we calculate and try to look them up if we've already calculated them. So, since we're always going to try and first look up the answer if we have it, the very first thing we do whenever we call Fibonacci mem is check if n is in our dictionary of results. In other words, have we already calculated the nth Fibonacci number? If so, we'll just return the result we've already calculated, which we've stored in the dictionary at key n. Then we proceed similar to how we did before. If we have a 0 or a 1, we already know the answers for those particular numbers. They're just exactly defined. Otherwise, we have to make the recursive call and calculate the previous numbers in the sequence. But once we've calculated this answer, whatever it is, we store that in our dictionary before returning the answer. So by doing this, we can short circuit this recursive call in many cases, because, for example, once we calculate Fibonacci 2, then we'll have it stored in our dictionary D, and whenever we call Fibonacci 2 again, we can simply look it up in the dictionary and return that, rather than make this recursive call, which is relatively expensive. Looking up values in a dictionary is extremely fast, as we've discussed in previous lectures. So that's all well and good in theory. Let's test it in practice by comparing how long it takes to calculate the 33rd Fibonacci number using a memoized algorithm, as we just implemented, versus the recursive algorithm. So on average, it ran this function 100,000 times, and it found it took on average about 15 microseconds to calculate the 33rd Fibonacci number when we were using the memoized version of the algorithm. Meanwhile, the recursive solution took on average 1.7 seconds. So it was about 10,000 times slower. Or actually, it's about 100,000 times slower than the memoized version. This is a huge difference. In terms of how long we have to wait around as users, there's not a huge difference between 15 microseconds and 2 seconds. But if we have to run this function over and over and over again, say 1,000,000 times, 1,000,000 times 10 microseconds is 10 seconds. 1,000,000 times a second is 11 days. So often when we're benchmarking functions like this, we're not only paying attention to how long it takes to run the function once, but we're thinking about what if we need to run the function many times, like 1,000,000 times. And then these relatively small differences in terms of our experience can magnify into very large differences. So yeah, the Memoized version is 100,000 times faster. That's a huge speed up. And just to prove it, the two functions give the same result as well. And we could put an assert here to assert that this is true. And nothing happens, so we know that this is true. Now, we didn't get this for free. We didn't get this speed up for free. We paid a price. And that price was this dictionary that we have to carry around. We're now using a data structure, and therefore we spent some amount of memory storing these results. Now, the payoff is that we clip down or excise a huge part of this tree. This tree becomes essentially linear. I go from 5 to 4 to 3 to 2 to 1 and 0. And then once I've calculated, I hit 1 and 0, which I know the answers for, and then I start marching back up here to 2, then to 3, and I already know 2 and 1, so 3 I get for free. 4, I already know 3 and 2, so I get 4 for free. And then 5, I already know 4 and 3, so I get 5 for free as well. So we take this exponentially fast growing tree and reduce it to essentially a problem that's linear in n. So for the cost of a data structure that is linear in size with n, right, we only have to store the result for the Fibonacci numbers 0 through n, so it's linear in size with n. We get a speed up in computational complexity from exponential in n to linear in n. That's huge. So we did make a trade-off, but a very worthwhile one. So at this point, I'd like you to pause the video and complete these exercises. First, write a factorial function that will compute the factorial recursively. If you're not familiar with factorial as a mathematical operation, you can simply Google it. So 5 factorial is 5 times 4 times 3 times 2 times 1. And you may notice you can also define 5 factorial as 5 times 4 factorial, because 4 factorial would be 4 times 3 times 2 times 1. N factorial, in other words, if I write it out, n factorial equals n times n minus 1 times n minus 2, and so on, down to 1. Whoops. Let's make these asterisks, I guess. No. Trying to remember my symbols. All right, let's just use dots. Hopefully you're familiar with this dot notation means multiplication. So I have n times n minus 1 times n minus 2, and so on, down to 1. Actually, if I'm just putting all of these in parentheses, I can just have it like this. And excuse me, looking at this, we can observe that If this is n factorial, then n minus 1 factorial is n minus 1 times n minus 2 times n minus 3 all the way down to 1, which means n factorial equals n times n minus 1 factorial. So here we have something that looks like a recursive function. Because n factorial is equal to something times the exact same thing that we're interested in, the factorial. So write a factorial as a recursive function. Then consider the following two questions after you've done that. Ask yourself, would memoization improve this function? Would it give us an efficiency boost like it did for the Fibonacci sequence? And whatever you determine, would decide whether or not memoization would be useful if we need to calculate the factorial multiple times. So pause the video here and complete those exercises, and then unpause and I'll share my solutions. Okay, so I can define a factorial function for n, and if n is 1, this is going to be my base case. If n is 1, I return 1. I know the factorial of 1 for sure. No problems there. And in fact, I'll make this 1 or n equals 0. I'm not going to consider negative numbers because factorial has a sort of funny different definition for negative numbers. So I'm not going to be considering that here. But for positive numbers, if n is 1 or 0, then factorial returns 1. And we can see that in this table here. Now, I can otherwise return factorial, or n times factorial n minus 1. Exactly this recursive formula that we have written here. So n factorial we can write in terms of a factorial. So we'll simply create that recursive call. So factorial 5 is 5 times 4 times 3 times 2 times 1, and that's 120. And we can even check, there is a factorial function. I actually didn't want to do that. Let's just import math. So we can check that my factorial function is equal to the official or factorial function included in the math module in the Python standard library. And we'll just check that they give the same answers. So for numbers 0 through 1,000, this assertion ran without raising any errors, so we know that my function is giving the same as the math.factorial function. Now let's think about whether or not memoization would, if there's a way to use memoization to improve this function. Remember, when we were talking about the Fibonacci sequence, the advantage of memoization was that we were recalculating results many times. 3 we calculated twice, 2 we calculated 3 times, and we wanted to store those results so that we don't calculate these results many times, but instead can just look them up and only calculate them once. For factorial, we're in a slightly different situation. N factorial is equal to n times n minus 1 factorial. N minus 1 factorial is n minus 1 times n minus 2 factorial. So we can see that what we end up doing is exactly this expansion, n times n minus 1 times n minus 2, and so on until we hit 1. And we never calculate any factorial twice, or more than once. We calculate each factorial in this chain of recursive calls exactly one time. Because 5 times factorial 4 becomes 5 times 4 times factorial 3 becomes 5 times 4 times 3 times factorial 2. We're not getting any repetition here. And for this particular mathematical problem, we won't, because there's one recursive call, and it just linearly expands on itself. So there's no way to use memoization to improve the time complexity of this algorithm. Where memoization could help us is if we need to calculate a factorial more than once. So obviously, if I call factorial 5 and then I call it again, I'm doing a new calculation every time I run that. So another way in which we can use memoization in our programs generally is if we expect to be calculating a lot of the same results with a function over and over again, we may want to store those results in a data structure and look them up in the future. This was the idea of a lookup table that we introduced in the data structures lecture. So I'm going to conclude the video here, and then we'll have one more video in this notebook. It'll be a short one about memory complexity.